Hello dear students, this is Professor Anindo Dash from Achievers and welcome to my lecture series on chemical kinetics. Now the very term chemical kinetics. What does this mean? At first you have to understand the meaning of chemical kinetics, the objective of chemical kinetics. So here we involve the term kinetics. Kinetics is something related to rate. Kinetics is something which is related to rate. And rate is something which is related to time. So let us begin the concept of chemical kinetics from the very grassroots level, from the very fundamental level. So for that purpose, what we need to do, we need to choose a reaction. Let us choose a reaction like R moving on to P, product. R is a reactant which is moving on to product. A simple reaction is chosen over here. Now the very first question a physical chemist will ask is whether this reaction is at all feasible in nature. So the very first question a physical chemist will ask is whether at all this reaction is feasible in nature. Whether this reaction is at all feasible in nature. So this is the very first question a physical chemist is going to ask. And how can we answer this? How can you answer this question? The answer is deep-seated into the concept of thermodynamics. So this will be answered by thermodynamics. This will be answered by thermodynamics. We will measure the change in Gibbs free energy for the reaction under the constraints of constant temperature and pressure, and we'll see whether it is negative or zero. If it is negative, the reaction will be occurring spontaneously. And if it is equal to 0, the reaction is said to attain the state of equilibrium. What if delta G is positive? If delta G is positive, then the reaction is not at all feasible in nature. That's it. So the very first question is to ask that whether this particular reaction that I have considered is at all feasible in nature. And that will be answered by thermodynamics. So thermodynamics is the dictating subject which will confirm whether the reaction or any physico-chemical process under consideration is feasible at all. Okay. So, for the feasibility of any physico-chemical process, thermodynamics will basically be dictating the deciding parameter. Okay. So let me repeat what I have taught till now? You have got a reaction. So the very first question of physical chemistry is going to ask is to whether this reaction is at all feasible in nature or not. And that will be answered by the subject thermodynamics. In thermodynamics, we have a physical parameter G, which is nothing but Gibbs free energy. So you have to calculate the change in Gibbs free energy for that particular physico-chemical process under the constraints of constant temperature and pressure. And if the change is negative, that means the Gibbs free energy is decreasing. It means that that particular physico-chemical process is feasible, is spontaneous. And if it attains the value 0, that means Gibbs free energy attains constancy under the constraints of constant temperature and pressure. Delta G is 0. The change is 0. That means G is constant. Under that condition, the process is said to attain the state of equilibrium. And if the change is positive, then the concerned physico-chemical process will not proceed in the forward direction, rather it will proceed in the backward direction. In short, we can say that the concerned physico-chemical process is not feasible in nature. So this is the very first question that is being asked. And if the answer is yes, answer to what is yes? Answer to the feasibility is yes. Yes, it's feasible. Then the next question that arises is, what is the rate of the process? What is the rate of the process? So at first the question that is asked is whether the process is at all feasible in nature or not. And if the answer is yes, yes it is feasible in nature, then the next question that will be asked is, what should be the rate of that particular process? Okay. And this will be answered by chemical kinetics. Chemical kinetics. This will be answered by chemical kinetics. It will determine the rate of the process. It will determine the rate of the process. The rate of the process. So, thermodynamics answers the question of feasibility, and chemical kinetics answers the question of the rate. I mean to say, for a particular process, at first thermodynamics is intervening. And thermodynamics is answering the question of feasibility. Or it is answering the question to what extent the process will proceed. To what extent the process will proceed. The process will proceed. To what extent the process will proceed. That means, in short, it answers the question, how far? It answers the phrasal question, how far a process is going to proceed. It answers the question, how far. Next, The subject chemical kinetics is coming. When is it coming? If the process is not feasible, then it's not worthy to ask what is the rate of that process. The question will be meaningless. So at first thermodynamics will filter whether at all this process is feasible in nature or not. And if the answer is yes, if feasible in nature, then the next question that is coming is what is the rate of that process? And that will be answered by chemical kinetics. So chemical kinetics answers the question, what is the rate of the concerned process? What is the rate of the concerned process? Okay. What is the rate of the concerned process? In short, it answers the question, the phrasal question, how fast? So in short, if you have a reaction like this, then you ask just two questions. At first you ask the question to thermodynamics, how far? That means whether the process is feasible or not, to what extent the process will proceed. And then if it is feasible, then you ask the question once again, how fast? And that will be answered by the subject chemical kinetics that will determine the rate of the process. So a particular physico-chemical process is subjected to two fundamental questions. The first question, the question of first priority is how far? And if the answer is affirmative, then the next question is how fast? These two questions are to be answered in context to a particular physico-chemical process. And now in this particular subject, we will solely focus into this particular question, that is how fast. That means we will deal with the rate of the process. So time, the parameter time, is going to play a very pertinent role in this particular subject. Okay. So let's proceed a bit. Some fundamental or rudimentary steps in context to chemical kinetics. So we would be discussing some rudimentary steps. In context to chemical kinetics. Some rudimentary steps in context to chemical kinetics. So we'll discuss this thing. Step 1. At first, you have to make a choice of the reaction. So the very first step is choice. You have to choose a reaction. Choose a reaction. You have to choose a reaction and represent the same by time independent stoichiometry. So you have to choose a reaction and represent it by time independent stoichiometry. By this phrase, time independent stoichiometry, I mean to say that once you specify the stoichiometry of a reaction, you can't change it unless and until the entire analysis with respect to chemical kinetics is over. So you have to choose a reaction, say nitrogen plus 3H2 2 ammonia. So you have specified the stoichiometries of, for nitrogen it's 1, for hydrogen is 3, and for ammonia it's 2. So you have balanced the reaction, you have specified the stoichiometry. So you can't change this stoichiometry unless and until the reaction, I mean to say the analysis of chemical kinetics for that particular reaction is over. So you have, say you have taken this reaction. So you have ascertained that the stoichiometry of nitrogen is 1, that for hydrogen is 3, and that for ammonia is 2. So you have ascertained that. And you can't change these factors unless and until the entire analysis with respect to chemical kinetics is over. You must stick to this fact. You could have chosen the stoichiometry 2, 6, 4. But once you write it in that way, 2, 6, 4, 2N2, 6H2, 4 ammonia, then you have to stick to that unless and until that particular analysis with respect to chemical kinetics is over. So you can't change the stoichiometry in the middle of the analysis. That's what I am trying to say. It might seem that these points are not so significant, but this is very important, my dear friends. This is very important. This is utterly important in context to the concept of chemical kinetics. And I will gradually reveal the things as I proceed further into this subject. Okay. So this is one of the most important topics in context to physical chemistry. And for that reason, you must be aware of every nuances of this subject. You can't ignore a trivial thing. You can't ignore any trifling things. You can't ignore any trivial thing or any trifling things. You have to take into consideration all the minute details. Okay, because a subtle change in the language can cause a huge error in the subject. So you must refrain from doing so. You must have a clear-cut knowledge about the subject, clear-cut concept about the subject. And that's why these concept clearing lectures are so important. Okay, so at first you need to build the concepts. You must clarify the concepts so that you can enter into the realm of volley of questions and you can answer any question provided your concept is absolutely clear. So it's high time. Tighten your seatbelts and plunge into the deep ocean of chemistry over here. And here the ocean is chemical kinetics. It's a deep ocean. You have a lot to understand. So from the very beginning, I would like to tell that you must not avoid or just ignore any trifling details. That's what I am trying to say. So this is the first point. The first point deals with the choice of a reaction, how to choose a reaction. Now, I'll be moving into the second point. In the second point, you need to monitor the variation of mass or any mass dependent quantity with respect to time. What does that mean? I'll explain it later. At first, let us write. So, the second point is monitoring the variation of mass or any mass dependent quantity of the species involved in the reaction with respect to time. So, you have chosen a simple reaction, R moving on to product. So, either you can monitor the variation of mass of R with respect to time, it will gradually decrease, or you can monitor the variation of mass of P with respect to time, the product will gradually increase in mass. So you can directly monitor mass, or you can monitor any mass dependent quantity. What are the mass dependent quantities? You see, what are the mass dependent quantities? It can be number of molecules, number of moles, or concentration. How? We all know that number of moles N is equal to mass by molar mass, which is equal to number of molecules by Avogadro number, and concentration is number of moles divided by volume. So, the molar mass, Avogadro number and volume, these are constants. Will maintain constant volume. These are constants. Constant volume of the medium. Will maintain constant volume of the medium. So these are constant factors. So you can see mass is directly proportional to number of moles. Mass is directly proportional to number of molecules. Again, number of moles is directly proportional to concentration. So one can say that mass is directly proportional to number of moles, is directly proportional to number of molecules, is directly proportional to concentration. So either you monitor mass directly with respect to time, or you monitor any mass dependent quantity with respect to time, that can be number of moles, number of molecules, or concentration. Conventionally in chemical kinetics, we choose this parameter, concentration, and we monitor the variation of concentration with respect to time. So we will monitor the variation of concentration with respect to time. That means concentration as a function of time. This is monitored experimentally. Okay, so this is our second point. Now a third point is from the data we obtain in the second point, that is concentration as a function of time, we will develop a rate equation or a rate law. So from this data, we will experimentally obtain a rate law. So from this data will eventually yield, this data will eventually yield the rate equation, which is also known as rate law. Okay. So these are the two steps, step 2 and step 3. These are the experimental steps. These are the experimental steps. So point number 1 deals with the choice. Point number 2 and 3 together deals with the experiment. There are 5 steps in total. So now we'll be moving on to step number 4. Now from the kinetic data, from the experimental kinetic data, the mechanism of the concerned reaction will be predicted. So from the experimental kinetic data, the mechanism of the reaction is predicted. The mechanism of the reaction is predicted. From the experimental kinetic data, the mechanism of the reaction is predicted. From the experimental kinetic data, the mechanism of the reaction is predicted. So, you can say any mechanism in inorganic, organic chemistry is always supported by the experiments of chemical kinetics. Without the experimental support or experimental evidence arising out of chemical kinetics, one can never ever predict the mechanism of a reaction. So the prediction of the mechanism of any chemical reaction is envisaged from the data obtained by chemical kinetics. Okay, the kinetic study. Now, the 5th point that is coming is deduction of the rate equation from the above predicted mechanism. So we have obtained the rate equation experimentally. Now again we are mathematically deducing the rate equation from the above mechanism and eventually compare with the experimental rate equation. So in the 3rd step, we have already obtained the experimental rate equation, and from the kinetic data, you have predicted a mechanism, and from the mechanism, once again, you mathematically deduce the rate equation, and then you need to compare the 2 rate equations. Okay, and if the rate equations match together, closely match together, if they resemble each other, then you can say that the mechanism you have predicted is absolutely correct. But if there is a difference, if there is a deviation, then you can say that the mechanism is not perfect. You need to modify that mechanism. That's what is the process of any chemical research in terms of kinetics. So the first point belongs to the choice. The second and the third point belongs to the experiment, and fourth and fifth point belongs to theory. Fourth and fifth point belongs to theory. Okay. So these 5 points will eventually control the entire subject of chemical kinetics. Okay. So with this introduction, we'll end our lecture today. Thank you all. Bye bye for now. Stay tuned. Bye.